All right, so this is going to be a relatively quick video, and it's just discussing two quick exceptions to our octet rule. And so, usually we like to say that when we're building different Lewis structures, we like to have, 8 electrons around everything. But one atom that typically tends to break the octet rule is something like boron. And what it ends up doing is it forms an incomplete octet. And so I'm giving here two different structures of boron. I have BH3 and BF3. And so when we built the Lewis structure here for boron, boron brings in 3 electrons. Each hydrogen brings up 3 electrons. So for BH3, that's 6 electrons. So we've used up all of our electrons. And this is kind of a happy state for boron, because if we look at formal charge, boron likes to have 3 valence electrons. It has 0 lone pairs. It has 3 bonds, so it has a formal charge of 0, and the same is true for each of these hydrogens. BF3 looks very similar to BH3. Boron brings in 3 electrons. Each fluorine brings in 7, so that's 21. So 3 plus 21 is 24. We spend, 6 of those electrons in bonding, and then 18 of them in forming our lone pairs around fluorine. And if we look at our formal charge here, boron has 0, and each of the fluorines. Fluorine likes to have 7 electrons, and right now it has 6 electrons in lone pairs plus 1 bond. So this fluorine also has a formal charge of 0. And so each of these, which I'll do them in red now. So each of these is a formal charge of 0. So this and this we'll do is 0 and 0, and these are formal charges. And then I'll do the same here, here, and here, and here. So this is 0, this one's 0, this one's 0. I did 0 twice on that one hydrogen. But all of those have a formal charge of 0. And so if you look at trying to give, in the case of BF3, which is actually capable of doing multiple bonding, as opposed to BH3 where we had used up all 6, if you look at trying to take those electrons from one of these fluorines and forming that double bond to give boron an octet, and to give us something that looks like this, where we've lost one of our lone pairs, now what we end up with in terms of a formal charge argument is that boron now it likes to have 3, and it has 0 lone pairs and 4 bonds. So now this boron has a formal charge of -1, and this fluorine, which typically likes to have 7 electrons, has 4 electrons in lone pairs plus 2 bonds, so it has a +1. And so in this case, although we get to an octet, we have a very highly charged molecule in terms of formal charge. And then the biggest reason that we don't like this is we've tried to put a +1 formal charge on fluorine. So, and we know that fluorine is most electronegative atom. And because of that, it's very unlikely to give up those electrons. So it's not really going to form that double bond, because it's just going to keep those electrons to itself. So very unlikely to give up electrons, and then especially have that positive formal charge. So in the case of boron, because it gets its happy state when it has 3 bonds and 6 electrons, we typically let boron have 6 electrons. Boron happy with 3 bonds and 6 electrons. And so where we have cases where we don't get to an octet, we also have cases where we expand the octet. And this is for elements that are in the 3rd row and beyond of the periodic table. So things like phosphorus, sulfur, and chlorine. And in these cases, what's happening is these 3rd row elements are putting electrons into the close d orbital. So put electrons in d orbitals. And when I say an expanded octet, what I'm talking about is that each of these is getting, I'm just going to loop it down here, 12 to 14 total electrons. that it gets to quote unquote own. So it's going to form, forming in most cases more than 4 bonds. And so one example of this is SF6, sulfur hexafluoride, where when you draw the Lewis structure for this, sulfur gives you 6 electrons, each fluorine gives you 7, and you have 6 of those, so that's 48 total electrons. And if you put sulfur in the middle and then put all 6 fluorines surrounding it, what you end up with is that you use all 48 electrons by forming single bonds to sulfur and then putting the octets around fluorine. Another example of this is sulfate. So we drew this Lewis structure right here when we're looking at examples for drawing Lewis structures. But if we look at this structure and we look at formal charge specifically on each of our atoms, we can see that each of these oxygens owns 1, 2, 3, 4, 5, 6, 7 electrons. We know that it wants 6 total electrons, so this has a formal charge of -1. And that's true for every single oxygen. And then sulfur also wants 6 electrons, but it has, it has no lone pairs and it forms 4 bonds. So this sulfur has a formal charge of +2. And so what we'll see is that in able to reduce formal charge, 2 of these oxygens are going to give up their lone pairs. So let's say it's this one and this one. And when we do that, what we get is the structure to the right, where we now have double bonds between the sulfur and 2 of the oxygens. And if we calculate the formal charge here, the 2 oxygens that didn't change still just have a -1. The 2 oxygens that did change, though, now they have 1, 2, 3, 4, 5, 6 electrons. Oxygen wants 6 electrons, so this has a formal charge of 0. Same is true here. And then our sulfur, it wants 6 electrons. It has 0 lone pairs, but now it's forming 6 bonds instead of 4. And so this has a formal charge of 0 as well. And so by forming those double bonds, we actually have given ourselves a structure that is more correct because it minimizes formal charge. And so when you see this on an exam and I ask you to draw something like sulfate, you'll draw it in a form that minimizes the formal charge. So you'll draw it in this form right here. Okay? And we can also use this form of sulfate to justify why it forms something like sulfuric acid and what that structure looks like as well.